Okay, so now this is going to be a math lecture, and this is going to be a review of complex numbers and complex valued functions of real variable. I'm going to use a separate color just to separate. This is a different subject. So complex numbers they are made up of a pair of real numbers. C equals A plus IB. For example, complex number C equals 3 plus 2I. This is called a real part, and this is called imaginary part. Okay, and what is I? Well, I equals the square root of -1. It's a quantity that does not exist in the set of real numbers because there is no such real number that when you multiply it by itself, it gives you a negative number. So mathematicians invented, they expanded, they opened up a whole new dimensions of numbers and called them complex numbers. Complex numbers can be visualized in a complex plane. This is called the real axis. This is called the imaginary axis. If you have a complex number C, it has a real part A, has a real part, and imaginary part B. Now a complex number, as you can see, it's almost like a vector. It's kind of like a two-dimensional kind of a number, and it has a magnitude or amplitude. Some people call it magnitude, some people call it amplitude. I sometimes mix the two terms. It's denoted like that. And there's a Pythagorean theorem. Okay? So C itself is a complex number, but the square of its magnitude obeys the Pythagorean theorem. It's the square of A plus the square of B. Now, so C has a magnitude, right? So this is right here. This is the magnitude of C. Okay. And there is an angle to speak of. This is called the phase. Sometimes, I think sometimes it's called, I think there's a notation for that, but no, I just call it phase. Okay. So note that A, the real part, is the magnitude, is the cosine of phi. The imaginary part is the magnitude times the sine of phi, just trigonometry. And B over A, the imaginary part of the real part, equals the tangent of phi. Okay. For example, let's say you have a complex number. I'm going to call it Z. Oftentimes they use letter Z for a complex number. I called it C. I'm going to call it Z. Okay, just so you get used to it. Z equals 3 plus 2I. What is the magnitude of Z? The square root of 3 squared plus 2 squared. That's 9 plus 4. It's square root of 13. And phi, so you went 3 plus 2I, so it's something like this. It's less than 45 degrees, so it's tangent inverse of 2/3. Okay. Now here's the big brouhaha. It's called Euler's formula. I think it's called Euler's formula. Let me double check. Just a second. Yes, it is called Euler's formula. And that's a big deal. Okay, to emphasize how big a deal it is. E to the I phi equals cosine of phi plus I sine of phi. It doesn't follow from what I said so far. It's a new piece of information because I dragged an exponential into it. Okay, I'm not proving it. If you want the proof, try for yourself. Taylor expand e to the I phi. And then collect all the real coefficients, all the real terms, and collect all the imaginary terms. And you will see that all the real terms add up to the Taylor expansion of cosine. All the imaginary terms add up to the Taylor expansion of sine. Now, I get the impression that this is not taught in high schools anymore. The emphasis is no longer on high quality education. But when I was in school, this was taught in 11th grade. It was a very big deal. It's completely invaluable. And I remember last year, I taught a similar lesson on complex numbers. And then it came to the final exam review, and this one student was very frustrated. Further on, the class is getting more and more mathy, and you have to use the tools that I'm giving you. And this guy said, well, I don't know, I've never seen anything like this. How was I supposed to know that I was supposed to use that? Here's how. There's a reason I'm doing this lesson at this hour, at this stage of the class, okay? This is important. And in your homework, I decided to put a little boot camp, complex number boot camp where you practice these things, okay? So, if you have a complex number that has a magnitude 1, you can write it as e to the I times its angle, times its phase. And if you have a complex number that has a magnitude other than 1, well, you can also write it using this notation. So notice that magnitude of a complex number times e to the I phi equals magnitude of the complex number cosine of phi plus I times the magnitude of the complex number sine of phi. And you recognize that this is just A, the real part, and this is B, the imaginary part. So a complex number C can be written as C equals its magnitude times e to the I times its phase, which is the same as its real plus I, its imaginary. So this is magnitude, phase, form, and this is the real imaginary form. This one and the same complex number can be written in both forms. Let's try. I'm going to give you a complex number z equals, say, 7 plus 5i. So this is a real imaginary form. Let's find the amplitude and the phase form. Well, so first of all, we need z equals square root of 7 squared plus 5 squared. That's 49 plus 25. Just a second, I'm going to get the pure number out. So I got the decimal. So this is what? 74, and that's approximately 8.6. Okay, that's the magnitude. And now let's get the, so tangent phi equals 5/7. Okay, so phi is approximately, tell you, 0.62 radians. So z equals 74 e to the I arc tan of 5/7, which is approximately 8.6 times e to the I times 0.62 radians. And you can depict it graphically if I give you either form, right? So if I give you 7,5, so it's somewhere here, okay? And this is right here. So this magnitude is 8.6, and this is 0.62 radians. Let's see if it makes sense. Well, 90 degree is 5/2, that's about 1.5 radians. So 45 degrees about 0.75 radians, and so this is less than 45 degrees. Yes, so this is right. So this is a real z, and this is imaginary z. And this is sometimes called the z-plane. Okay. Now, the next idea is something called complex conjugate. And so given a number z, sorry, don't mind that sometimes I'm using c, sometimes I'm using z. You should be comfortable with it, right? Z is a standard notation. Given a number z plus a plus ib, its complex conjugate z star is given by a minus ib. So i.e. z star, star means complex conjugate. And many times throughout this quarter, will you ask, what's a star? Why are you putting star on something? Oh, it's complex conjugate, okay? It's complex conjugate. So if I write something like psi and then a psi star, it's a complex conjugate. If I write something like A and A star, guess what? A star is a complex conjugate of A, okay? So yeah, there will still be reviews, angry reviews that say that I've never defined things and then I use random letters, random numbers, but just between us, it's a complex conjugate, okay? All right, so example, if z equals 3 plus 7i, z star equals 3 minus 7i. Now, how would you depict that? So here's the real plane. Here's 3, 7. So here's your z, number z. The z star has the same real component, but the opposite, or the negative imaginary component, right? So this is the real and this is the imaginary part. So this has angle phi. This is angle minus phi. So how would you write the z star in the amplitude phase notation? What should I write here? Well, it has the same amplitude, but the angle is minus of the angle of the z. Okay? And this is very useful. Note that z times z star equals z e to the I phi times z e to the minus I phi equals, and then you just distribute everything, z squared e to the I phi e to the minus I phi. Now you might remember e to the, I don't know, x times e to the y equals e to the x plus y. Just a little algebra review. So this is z squared e to the 0. And so what we learn is that if I give you two complex numbers, you can find its magnitude either using the Pythagorean theorem, and that's convenient if I give you the real and imaginary form. If I give you amplitude and the phase form, all you do is you multiply z by its complex conjugate. Z equals the square root of z star. And this is useful, you will see. But we'll do a lot of that with wave functions. Useful. Okay, so that's numbers. You can also have functions of complex variables. Functions of complex variables. Now, what is a function? A function is a machine into which you put a number in, you get a number out. Okay? So here's a f of x. You put f into, it spews out f of x. Sorry, you put x into, you put an x into it, and it spits out f of x. That's in general. So this is called, let's call it function f. Okay? That's a function called function f. You put an x into a slot here, out comes out a number called f of x. Okay? So example, this is just regular, right? So you f of x equals x squared. You put a 2 in, you get 4 out. Same is true for complex numbers. So you can have functions of complex variables. You put a complex number in, it gives you some other complex number out. Let me give you an example. F of z equals z squared. So this is a plus ib squared, that's a squared, minus 2, so plus 2 iab minus b squared. So the real part is a squared, so z equals a plus ib. So the real part of this function is going to be this concoction of the parts of z, its real part minus the imaginary part, plus I to ab. Now the good news is that in this class, we will not be dealing with complex valued functions of complex variables. We will deal with complex valued functions of real variables. Okay, so you have some kind of a function. You put a x into it, real, like position. and it spits out f of x, which is complex. Example, f of x equals x plus ix squared. Just came up with an example. So then f of 3, you put a number 3 into it, gives you a complex number out. Example 2. Now let's call some other function. Let's call it the g. G of x equals x squared e to the I x. F of 7 equals 49 e to the I 7. Why not? You can do that. Okay. Okay. Let me give you some more examples that are important. I need to add some pages, just a second. Okay. Example. So this is example, I guess, example 3. Now, if I give you something that looks like this, psi of x equals e to the I kx. What comes to mind? How does it make you feel? Well, you probably wouldn't think of this as a wave, but there is Euler's formula, which says that it's k cosine kx plus I sine of kx. Okay, so the real part of psi versus x is just a cosine wave. And the imaginary part of psi versus x is a sine wave. Incidentally, if I ask you, what is the wavelength of this thing? Wavelength is the distance over which the function repeats. So here, this is 1, and here it's 1 again. This is the wavelength. So k times the wavelength equals 2 pi, because a function repeats when its argument, this is called the argument of a function, increases by 2 pi. So here the argument is 0, here the argument is 2 pi. So here, k lambda equals 2 pi here. So this is just x, but when x is when x equals lambda, the argument is k lambda. So k lambda equals 2 pi. So lambda equals 2 pi over k. So I could write this as cosine of 2 pi x over lambda. And you can see when x becomes lambda, the argument becomes 2 pi. But it's a little bit cumbersome. And so it's easier to write it in this form. It's cleaner. And the thing that sits in front of the x is called the wave number. Okay, so this is called the wave number. Now, that's if x has the meaning of space. Example 4, what if it's a phi? No, phi is a bad letter because I'm using that for, let's see, psi, phi, I don't know, xi of time e to the I omega t equals sine, equals cosine of omega t plus I sine of omega t. So when the independent variable is space, the thing that sits in front of x, the location in space, is called the wave number. When the independent variable has the meaning of time, the thing that sits in front of the independent variable is called angular frequency. It's just a language, just a notation thing. Okay, so the real part of xi versus time is cosine. And the imaginary part, xi versus time, is the sine. It's not easy to write on an iPad. Okay, now this would not be a called wavelength. This would be called a period. Again, when we're dealing with time, we can ask about the period. When we're dealing with space or spatial coordinate, we can ask about wavelength. It's just a language thing. Well, what's the wavelength here? Well, it's such a period of time during which the argument advances by 2 pi. So omega times the period equals 2 pi. So period equals 2 pi over omega. Omega equals 2 pi over the period. And actually 1 over the period has a name of its own. It's called the frequency. Okay. There is no such equivalent for space. Wave number is 2 pi over lambda. Angular frequency is 2 pi over the period. Angular frequency. 1 over the period is called frequency, but there is no name for 1 over the wave. Anyway, language, language, language. These are all just language things. Okay? So this is called angular frequency. Now, your textbook does wonders at visualizing functions of complex variables. There are several ways to do that. If I have some kind of a g of phi equals e to the I phi, and let's say phi keeps growing. Now let me give you another example. Let me give you another example. Let's say that this is g of t e to the I omega t. Right, so at t equals 0, this is here, t equals 0. So this is a g plane. Okay, when t equals, so period equals 2 pi over omega. So at t equals 2 pi over omega times 1/4, we're here. This is t1. Okay, so at t2 equals 2 pi over omega times 1/2, we're here. This is t1, t2, t3, and t4. And so we are moving in a circle in complex plane. It's kind of an abstract idea, okay? But your textbook proposes another way to visualize that. Sorry. So this is the real G, this is imaginary G. And the way they propose to do that is they plot, this is the time, this is the real G, and this is imaginary G, and this is the real G. And they note that this is basically a corkscrew. Okay, so you follow a corkscrew in this space. Now, I'm not sure if this is actually helpful. When I was a student, I wasn't learning it like that. When you project, I guess the corkscrew is going in the other direction. I'm sorry. I think the corkscrew is, I think the corkscrew is going, I think I drew the corkscrew incorrect. The direction is that way. Okay, it's not going that way, it's going that way, like that. So let me fix that. But the point is, you can think of this as a corkscrew. Let me see if I can do it. It's hard for me to draw the corkscrew going in the C. Okay, so it's going like that. Okay, so it's going around and around. And if you project it on the real imaginary G-plane, you just get this. So it's just a visualization thing. I'm not sure if it's useful. Maybe it is. My point is that when you see this, or when you see this, I want you to say, aha, that's a wave. You have to recognize that this is a wave. That's what I want you to recognize. And finally, what if it is something like that? Let me give you, so I guess this is another example. I lost track of the examples. Some kind of a big psi, it's a function of both space and time, is e to the I kx minus omega t. Okay, well, that's cosine of kx minus omega t plus I sine of kx minus omega t. So that so now the real and imaginary part of psi represent traveling waves. At any moment of time, it's some kind of a spatial wave shifted by some kind of a phase constant, but that phase constant itself changes. So this is, so I can depict this as some kind of a, wave. And this is later time. By the way, if this is a minus, it's moving to the right. I hope you understand that. So this is T1, this is T2, and it's traveling to the right. The speed is omega over k. Okay. So this is sort of two different snapshots at different moment of time. I can also plot this versus time and look at two different positions at space. And then, so these are two snapshots. This might give you a little nightmare recollection from Phys 2. We talked about snapshot graphs versus history graphs. I no longer teach that when I teach Phys 2, but it's not going well with students. But this is an example of two snapshots, right? Snapshots at time t1 and time t2. I just take two pictures. But instead, I can sit at a given location, right? And I can visualize the history of that, of what I see as the wave passes by me. Imagine I sit here and the ocean wave goes. And I can draw a history experienced by me sitting at a particular location. I can sit at another location and I would experience a different history. Let's not dwell on that. Let's calculate some derivatives just for kicks. And then I have to go to office hours. So if I give you something like psi of x equals, notice this is a lowercase psi, this is an uppercase psi. E to the I kx, d psi dx equals ik e to the I kx, d squared psi dx squared equals ik squared e to the I kx, equals minus k squared e to the I kx, because I squared equals minus 1. If I have some sort of big psi of x e to the I kx minus omega t, I'm starting to use the letters that we use in quantum mechanics, lowercase psi, uppercase psi. I hope that does not add a layer of confusion. So I can take partial derivative of this with respect to x is e to the I k, e to the I k x minus omega t. And I can take the partial derivative of this with respect to time, which is minus I omega e to the I kx minus omega t. I sincerely, dearly hope that you don't just memorize these, that you actually try it on your own and understand why it is. Well, as you take the derivative of e to the ax, what do? You bring the a down. It's a chain rule. It's the derivative of the inside times the derivative of the whole thing. It's really just a chain rule. But the way it manifests itself is that you bring the a down. The way that chain rule would work is that you bring the a down and you leave alone the exponential. In this case, the a is just e to the ik, so that's why you bring the ik down. But again, it's really the chain rule. I want you to realize that this is a chain rule speaking. If you have a function of two variables, space and time, well, when I take the derivative with respect to space, right, you leave the time alone, because this is e to the I kx, e to the minus I omega t. I hope you understand that. And when you take the derivative with respect to space, this is just a dead weight. So it comes along for the ride. So all you have to do is you just have to take the derivative with respect to space, which you bring e to the ik down, and then you put them together again. That's why you get this. Okay. When you take the derivative with respect to time, now this is the live thing, and this is the dead weight. You take the derivative with respect to time, you bring this whole thing down, that gives you this, and you leave the exponent, and then you put the two exponents back together, and you get this. That's how I think of it. And one more thing, let's try g of x equals x e to the I kx squared. This is something else. Why don't you, well, you try it, pause, try it. Now I'm going to try it. So the chain rule, on the one hand, it's e to the I kx squared plus x times 2 I kx to the I kx squared. So it's chain rule, chain rule, chain rule, which is e to the I kx squared plus 2I kx squared e to the I kx squared. Guys, it's all it is. It is just a chain rule, right? So I applied the differentiation here. I brought the 2 down, multiplied, and so on. Okay. You will have to take some derivatives, but not so much integrals, so I'm not going to talk about integrals. And I'm out of time. So this was a little bit of a review of complex numbers, functions of complex variables. So by the way, let's say if I wanted to calculate the amplitude of g of x, well, that's x e to the I kx squared times x e to the minus I kx squared. That's just x squared. And if you were to graph this, first of all, it's not a regular wave because it's a wave whose wavelength is continuously getting shorter and its amplitude is continuously getting bigger. Okay. Okay. Well, that's a start. Okay, that will get you started. We will do a lot of math in this class from now on, so you really have to be very comfortable with complex numbers. when you have a complex number workout or a boot camp in your homework, please do it, okay? And tomorrow, we're gonna do a bit of physics, and then we will do a similar lesson on probabilities, because probabilities are important in quantum mechanics. All right, see you tomorrow.